All right, today I'm just going to go over the 5-1, 5-2 practice mastery quiz. Okay, so we went over it in class, but I want to make sure, just in case we went too fast, that you understand it. So I'm just going to go through the key. The key is posted in Schoology, so you can check that yourself, but I want to go through those questions. If we can answer these questions, then we're in really good shape for 5-1 and 5-2. Okay, if we understand the concepts there, and then that'll lend itself right into 5-3 when we start talking about buffer solutions. Okay, so let's get into it. So here's the 5-1, 5-2 practice mastery quiz. All right, so there's 6 questions here, but let's go ahead and dive into it. Okay, so question 1, it says, what is the pH of a 0.435 molar solution of perchloric acid? Okay, so we have to go, hey, wait a minute. If they give us the molarity of an acid, if we want to find the pH, they also have to give us the Ka if it's a weak acid. So we need to recognize, oh, wait a minute, perchloric acid is one of our strong acids. So this is really easy. The molarity of the acid, which is 0.435 in this case, is the molarity of H+. So for question 1, all we have to do is take the negative log of that molarity, and we recognize that that is the molarity of either H+ or hydronium, because that's a strong acid. So we take the negative log of that. So the pH would be 0.362. Okay. All right, let's go to number 2. All right, so this is asking us the pH of a potassium hydroxide solution. So when it comes to strong bases, essentially it's just any metallic hydroxides, so ionic compounds with hydroxide. All right, so again, when ionic compounds dissolve, they're automatically dissociated. So if this is the molarity of potassium hydroxide, of a solution of potassium hydroxide, that means all of the KOH has dissociated. Salts, in order to be in solution, they have to completely ionize, right? It's not like the difference between strong acid and weak acid. Weak acids and strong acids are both dissolved in solution, but the question is, have they dissociated? Ionic compounds always dissociate. If they're in solution with water, they have broken up into their ions. So this one's pretty easy. We need to recognize if that is the molarity of this salt solution, then that times 1 would be the molarity of potassium ions, but that times 1 would be the molarity of hydroxides, because for every one of these, we have 1 hydroxide. So we have the molarity of hydroxide. So let's understand, if we take the negative log of this, that'll give us the pOH, and then all we have to do is subtract from 14 to get the pH. So again, we have to recognize that, oh, okay, that's just the molarity of hydroxide, because it's a 1-to-1 ratio. So the negative log of this is going to give me my pOH, and then if I subtract, so that's the pOH of the solution, but if I subtract from 14, that gives me the pH. Now, because I have 3 sig figs here, I'm allowed 3 decimal places when I report my pH value. Okay? All right. Let's move on to the next one. All right, so now we have a weak base, and they give us the Kb. All right? So ammonia is a weak base. We should memorize that ammonia is a weak base, but anytime you're given a Kb of something, that means that something is a weak base. So you're given Kb, that means weak base, and so they're telling you ammonia is a weak base here. All right? And so the first thing is we want to write the reaction of ammonia acting like a base with water, and then write the Kb expression. So remember, the Kb expression would be the equilibrium expression for the reaction we write in part A, right? So let's do A and B here. All right, so A would be ammonia plus water. So the H plus from water would go to ammonia to produce ammonium, and then you would get hydroxide. Remember, acting like a base in water means producing hydroxide. So we know hydroxide's got to be our product. So how do we get hydroxide? Well, the water has to give up an H plus to the ammonia, and that's how we get ammonium. All right, and we should use a double arrow because it is a weak acid, not a strong, or sorry, a weak base, not a strong base. Okay, so here is our reaction. And so remember, when you show a base acting like a base with water, the equilibrium expression for this reaction is the Kb. So we would say Kb equals, and it would be products over reactants. And remember, we don't use water because that's the liquid, that's the solvent. So we didn't need our states of matter here, but if you wanted to know, it would be aqueous, liquid, aqueous, aqueous, right? So that's what we're using here, okay? And so remember, we were given the Kb value, so that's what Kb is equal to, so we could take that number there, the K, and plug it in there, okay? All right, so part C is asking us for the pH of a 0.1 molar solution of ammonia. So we know ammonia is a weak base. We have the molarity of the ammonia in our solution. So this is a Kb shortcut. All we need to do is use our Kb shortcut. So remember, that's Kb equals x squared over the initial concentration of the base. Remember, technically this would be base minus x, but we're gonna 5% rule the x and get it out of here. So we're just going to use our initial concentration, but technically this should be 0.1 minus x right here, right? But we'll just plug in our Kb value, x squared over 0.1. We're going to solve for x. Now what we have to remember is, what does x represent in our Kb shortcut? Remember, x represents the molarity of hydroxide. If we look at our equation, x would represent the molarity of hydroxide, and it would also be the molarity of ammonium in the solution, but we're not worried about that. We're just worried about the hydroxide. So we would figure out x, which would be the molarity of hydroxide, and understand, if we took the negative log of this, that would not equal the pH. The negative log of this would equal the pOH, because that's the hydroxide concentration. So we have to subtract from 14. And so our pH is 11.128. Now, technically, I probably should have just said 11.13 because the Kb we used only had 2 sig digs. So 2 sig digs should be 2 decimal places in my pH measurement. So I should say 11.13 here, okay? And let's go back and understand how our answer should make sense, right? What is the pH of an acid solution? Well, it should be less than 7, right? What is the pH of a base? Well, it should be greater than 7, right? So again, ammonia is a weak base. So the reason I'm saying that is, if you got to, if you were doing part C and you got X, and then you took the negative log, and the negative log of this number is going to end up being less than 7, and you said that was the answer, that should be a red flag to you, because you know ammonia is a base, so you know the pH of the solution should be above 7. So when you take the negative log of this and it's below 7, that should be a reminder, oh, wait a minute, I better subtract from 14, because this pH makes more sense when you're talking about a basic solution, right? Okay. So part D. What is the pH of a 0.1 molar solution of ammonium? Now, this question, there's a lot going on to be able to answer this question, right? We got to be careful, all right? Number 3 starts with the fact that they give us the Kb of ammonia. Understand, whenever you're given a Kb of a weak base, you also can calculate the Ka of its conjugate acid, right? Because Ka times Kb equals Kw, and we know what Kw is, 1 times 10 to the negative 14. So this right here, they gave you the Kb of ammonia, but also they gave you the Ka of ammonium. You just have to calculate it, right? They gave you a way to figure out the Ka of ammonium, all right, which is a weak acid. And we know ammonium has to be a weak acid because its conjugate base, ammonia, is a weak base. In the conjugate acid of a weak base is a weak acid. So we know ammonium is a weak acid, all right? So the other thing to understand is, this solution here has nothing to do with this solution, just the one that we were talking about previously. It's just that we have to understand that ammonium and ammonia are conjugates so we can get the Ka of ammonium. So all this question is a weak acid shortcut question. All we have to use is our Ka shortcut, but we have to know how to calculate the Ka, and we have to recognize that we can calculate the Ka of ammonium because we were given the Kb of its conjugate pair, okay? So again, all it is a weak acid shortcut, Ka shortcut. All right, so if we do Kw divided by the Kb of ammonia, that gives us our Ka. So our Ka of ammonium is 5.6 times 10 to the negative 10, right? So ammonium, that shouldn't say weak base, that should say weak acid. That's frustrating. I'm mad that I wrote that. Anyway, so that's a weak acid, not a weak base. All right, so we'd solve for our Ka using Kw equals Ka times Kb. And again, because we've recognized that ammonium and ammonia are conjugate pairs. So that's our Ka, and we plug it into our shortcut. So Ka equals x squared over the initial concentration of our ammonium. Now remember, that would be minus x, but we're going to 5% rule that. So if we solve for x, x is in a Ka shortcut, x is the hydronium concentration, so the negative log of x is the pH. So we solve for x, we take the negative log, and we get our pH 5.13. Okay, all right. All right, so here is, they give us another hydroxide salt, and they give us the KSP for the salt. And we want to calculate the pH of a saturated solution. So when this salt has reached the point of saturation and in the dissolving process, we want to calculate what the pH is. And so notice that this is going to dissolve, it's going to dissociate, it's going to form hydroxide, but it's going to form 2 hydroxides for every one of the compounds that dissolves, right? So what we're going to do is use our KSP shortcut. So we would say KSP equals 4x cubed because it's a 1-to-2 ratio, and we would solve for x. Now, what would x represent in our KSP shortcut? It would represent the moles per liter of this compound, but to get the moles per liter of hydroxide, we'd have to double it. So we're going to solve for x, but then we're going to double it to get the molarity of hydroxide. And once I have the molarity of hydroxide, I can negative log that to get the POH, and I can subtract from 14 to get, to get the POH, and then I can subtract from 14 to get the pH, right? All right, so that's the process. Let's see it. All right, so again, I would say KSP equals 4x cubed to solve for the molar solubility. So when I solve for x, x comes out to be 0.0107 moles per liter. But remember, that's moles per liter of this entire compound. We'd have to double this to get the molarity of hydroxide because there's 2 hydroxides for every 1 mole of the compound. So we would double that, and that would be the molarity of hydroxide. So if we do 14 minus the negative log of that, that'll give us our pH. So we negative log this, subtract from 14, and we get our pH, 12.33. Okay. All right, let's keep on rolling. All right. So here we have a triprotic acid. What does that mean? It means 3 H pluses. And we're given the Ka values for each of the protons. So Ka1, that would represent the first acid dissociating. Ka2 would be the second, not acid, the first H plus dissociating. Ka2 would be the second H plus dissociating, and Ka3 would be the third H plus dissociating. And they want us just to show the chemical equations for each proton dissociation. All right, so let's do that. So the first dissociation, we get H plus and H2A minus. Then the H2A minus could dissociate. That would be the second dissociation. Okay. And then HA2 minus would yield 1 more proton and A3 minus. So this would be the first proton dissociation, the second proton dissociation, the third proton dissociation. So understand, Ka1 would be the equilibrium constant for this reaction, Ka2 would be the equilibrium constant for this reaction, and Ka3 would be the equilibrium constant for this reaction, okay? So part B just asked us what's the conjugate base of H3A. So all we would have to do is take away an H plus and from H3A, and whatever it turns into, H2A minus, that would be its conjugate base. Okay, so H3A and H2A minus are conjugate pairs. That's the acid, that's the base. Okay, now HA2 minus has 2 conjugate pairs. One where this is the acid and it has a conjugate base, and one where this is the base and it has a conjugate acid, right? So if we look at HA2 minus as a base and we want to figure out what its conjugate acid is, all we have to do is add an H plus to it. So if we add an H plus to it, boom, H2A minus, that's its conjugate acid. So that's one conjugate pair of Ha2 minus. And the other one would be its conjugate base, where you take an H plus away from it, and what it turns into A3 minus, that would be its other conjugate pair. So this is the conjugate acid of Ha2 minus, and this is the conjugate base of Ha2 minus. Okay. All right, so the last question, a lot of students will make this more complicated than they need to. So it's asking what the pH is of an H3A solution, right? So you have a weak acid, and you have the molarity of the weak acid. So we can't say take the negative log of 1 here because that's a weak acid. So that molarity is not the concentration of H+. But what we don't have to do is figure out how many total H pluses dissociate, right? So what some students will do is they'll say, okay, figure out what the H plus concentration is in this reaction, then figure out what the H plus concentration is from this reaction, and then figure out what the H plus is from this dissociation, and add those up, and that would be the total molarity of H plus in the system, and then take the negative log of that to find the pH. And yeah, technically that would be the most correct way of doing it, but that's really complicated. It turns into common ion question and all this stuff, and really what happens is the amount of H plus from the second dissociation and from the third dissociation, the amount of the H plus from those two dissociations is really small. Look at the values. It goes from 10 to the negative 6 all the way to 10 to the negative 10. So this dissociation is much less favored than the first dissociation. And look at the third dissociation, 10 to the negative 15. Even worse, not even favored. So these two numbers, the amount of H plus from this dissociation and the amount of H plus from this one, are going to be negligible compared to that. So all you have to do is use the first dissociation. So use your Ka shortcut for the first dissociation, use that K value, and you're good to go. All right, that's all you have to do. All right, so we would say Ka1 in this case equals x squared over the initial concentration of H3A. Remember, this was a 1, right? This was 1 moles per liter. That was the molarity, and this was the K. So we plug those in to the shortcut, we solve for x, and we take the negative log of x, because in a Ka shortcut, x represents the hydronium concentration. The negative log of x would be the pH. Okay. All right, and in class, we'll do an example of what you could do to make it a little bit more accurate, but I bet if we did find the other amounts of H plus from the second and third dissociations, I bet that when we took the negative log, it's going to be very close to 2.75. And when we round to significant figures, it might be exactly 2.75 again. So that's why, you know, it's good to simplify, because you're not really gaining much by not simplifying, okay? You're saving time by simplifying, and you're going to get the same answer as somebody who didn't simplify. Right? All right, so let's go to question 6. Okay, so it says hydrogen carbonate, HCO3 minus, is a weak acid when in solution with water. They give us our Ka. Now, let's think about it. Let's think about it. They gave me the Ka for hydrogen carbonate. So maybe later on in the question, I might need the Kb for its conjugate base. And its conjugate base would be CO3 2 minus, the carbonate ion, right? So maybe I'll need the Kb for carbonate later, and all we have to do to get the Kb for carbonate is do Kw divided by this, right? Remember, when they give you a Kb, you also are given a Ka, just kind of a little indirectly, right? And if you're given a Ka, you're also given a Kb, the Kb of the conjugate base. All right, so a student makes a 1 molar solution of hydrogen carbonate, okay? So first we're gonna write the reaction that shows this acting like an acid, and then we're gonna calculate the pH of the solution. So part B, we're just gonna do the Ka shortcut. Ka equals x squared over this concentration, the initial concentration of the acid. Okay, and then solve for x, and then take the negative log. That'll be part B, and then part A is just writing the equation. So let's do both of those. So hydrogen carbonate as an acid would have to be a proton donor. It would donate the proton to water. You get hydronium, and you would get carbonate. So notice carbonate, right there, CO3 2 minus, is the conjugate base of hydrogen carbonate. And so if we did Kw divided by this, that would be the KB of carbonate. We don't need that right now, but maybe we will later. Let's find out. All right, so that's our equation. Remember, if we wanted to write the expression, this would be a liquid, so we wouldn't include it, and it would just be that times that over that. That's what Ka would equal. All right, so to calculate the pH, we'll just use our Ka shortcut. Ka equals x squared over the initial concentration of the acid, 1 molar in this case. So I'd plug in my Ka value there, plug in my 1 molar there, cross multiply, take the square root, and then the negative log of x would be my pH, 4.22. Okay, so let's look at the rest of the question. A student makes another solution that's 0.1 molar sodium carbonate. Now, do I care about the sodium? Never, right? Sodium's just a spectator ion. It's neutral in solution. What I care about is that I have a 0.1 molar solution of carbonate. And we have to recognize carbonate as a weak base. How do I know it's a weak base? Well, it's the conjugate base of this acid, which is a weak acid. So I just made a basic solution because I just added a base to my solution. I added carbonate, okay? So maybe now I'm gonna need the Kb of carbonate. And I should recognize that I can get the Kb of carbonate based on the fact that they gave me the Ka for its conjugate acid, right? Kw divided by this will give me the Kb for carbonate. All right, so the first thing I'm gonna do is write the equation that shows sodium carbonate acting like a base, and really it's just carbonate. We don't need the sodium. And then calculate the pH. So to calculate the pH, it's just gonna be a Kb shortcut. We're going to solve for x, take the negative log of x, and then subtract from 14 to get the pH, because in a Kb shortcut, x is the OH minus concentration. But we just have to figure out what Kb is, and the only way I can calculate what Kb is recognizing that this is the conjugate acid of that base, and so I was given the Ka of this acid, so Kw divided by this would be the Kb of the conjugate, okay? All right, so first, the equation that's going on, carbonate's the base, it's taking an H plus away from water, you get hydrogen carbonate, and you get hydroxide, right? It's producing hydroxide, all right? So now all we have to do is a Kb shortcut. All we have to do is a Kb shortcut. We just have to calculate the Kb. So if I do 1 times 10 to the negative 14 divided by the Ka that they gave me, I get the Kb, 2.8 times 10 to the negative 6. So I'm gonna plug 2.8 times 10 to the negative 6 in for the Kb, and the initial molarity of carbonate is 0.1, so I'll plug that in there. I'll solve for x. I just gotta remember x is not H plus in this case. In this scenario, x is OH minus. I'll take the negative log of that, okay? That'll be the POH, and then I'll subtract from 14, okay? So plug in my numbers in my Kb shortcut. 14 minus the negative log of x will give me my pH, 10.72, all right? All right. So, easy peasy, right? All right, it's just knowing those concepts, right? All those equations are given to you. You just got to understand how to use them and what you're looking for, right? We got to start recognizing these anions as conjugates of weak acids, and so therefore they're weak bases. And if I'm given a Ka, I'm also given a Kb, or if I'm given a Kb, I'm also given a Ka, and using our weak acid shortcut or a weak base shortcut. But if you can do all those calculations, if you understand everything that was on that practice quiz, then you're in good shape for 5-1, 5-2, and in good shape for moving on to 5-3. Okay? All right, have a good one.